Since World War II, all of us on our planet Earth have had to think in larger terms. We began at last to look outside national boundaries and to see the world as the home of many countries. The earliest rocket flights suddenly brought space itself closer to us. We learned how to travel and to survive in that cold and alien place. For the first time, we looked upon our Earth as a sphere circling endlessly through space. Mankind's greatest adventure had only begun. It's through the development of rocket engines that we've been able to leave the Earth's gravity. No internal combustion engine can produce anything like the power required. A jet engine needs the oxygen of the atmosphere in order to burn its fuel, and therefore its altitude limit is about 17 miles. But a rocket can go anywhere in space because it carries both fuel and the oxygen in which the fuel burns. The picture is of a Saturn V rocket lifting off with an Apollo spacecraft on top. No event in history has captured the imagination of the world as did the American landings on the moon. The first, Apollo 11, landed July 20th, 1969, and from then until the end of the Apollo program in 1972, a total of 12 men walked on the surface of the moon. 3 of the missions carried a battery-powered automobile that roamed the lunar landscape. Skylab was launched unmanned on May 14th, 1973. Problems developed at once. During the launch, a meteorite shield ripped away, taking one solar panel with it and jamming the second. The lab was left without electrical power. Astronauts were sent up soon after, and in several spacewalks managed to improvise repairs. Power became available, and Skylab was saved. Skylab was a cylindrical station about 21 feet by 48, containing living quarters and laboratory. In a total of 3 manned missions to it, 75 major experiments were performed. 20 countries participated in a long series of Earth resources studies related to crops, minerals, underground water, sea currents, and the atmosphere. Since 1960, when America's first weather satellite was launched, we've all become used to the marvelous pictures from space that we see daily on TV weather forecasts. For many of us, this probably seemed to be our most direct and personal benefit from space research. But Skylab gave us many other benefits, less obvious perhaps, but every bit as important in our daily lives. The Mississippi River drains nearly half the nation. Each spring, melting snows and heavy rains can combine to cause disastrous flooding. The lives of millions are affected. Scientists studying space photographs like these of the river around St. Louis can help in planning for the protection of populated areas, engaging the effects of flooding on farmlands, and in locating suitable sites for future bridge and highway construction. Famine is mankind's greatest enemy. Using space photography, we can conduct worldwide surveys of crop production. Attacks by insects or disease can be spotted and dealt with long before they're apparent from the ground. Similar surveys can be made of fruit orchards, citrus areas, timberlands, and even mineral resources. In this infrared photograph of California's Imperial Valley, scientists can readily tell tomato fields from those of beans or alfalfa. The southwestern tip of Lake Michigan shows in black at the right. Chicago and other cities are light blue. The prevailing winds here blow off the lake, and as they pass over Gary, Indiana, a stream of puffy cumulus clouds is formed by hot air rising from the steel mills. The continuing formation of these clouds has doubled the amount of rain and snow here in recent years. Man has modified the weather, and this kind of ecological change can only be monitored from space. The Gulf Stream is a vast and powerful current of warm water flowing northward from the tip of Florida. Its exact boundaries may change radically from month to month, and constant surveying from space is essential. The stream can act like a conveyor belt for northbound vessels, saving both time and fuel. Nutrients along its boundaries and in its eddies attract great concentrations of fish, and locating them is important to the fishing industry. Engineers are even exploring the possibility of harnessing the stream to produce electrical power. One of the basic purposes of Skylab was to study the effects of long-term weightlessness on the astronauts themselves. The longest of the missions lasted 84 days, and there were no serious problems. Scientists were led to believe that space missions of at least a year would be feasible. Skylab, in summary, showed us what we can do in space. And with the shuttle as an economical way to get there, we can put all this knowledge to practical, everyday use. The Apollo-Soyuz mission of July 1975 gave the world dramatic proof that the United States and the Soviet Union could set aside ideological differences and cooperate on a joint venture in space. The two spacecraft were launched in their respective countries a few hours apart. This photograph was made through the window of Apollo as it maneuvered for docking with the Russian Soyuz. The spacecraft remained docked together for almost 2 days. In this model, they are seen joined by the universal docking mechanism. The astronauts from each country visited the craft of the other. By making it possible for two greatly dissimilar command vehicles to join together, the docking mechanism, in a sense, can symbolize present and future cooperation in space. It will not only permit a sharing of the enormous workload of space research, but it will also make international rescue missions possible if that should ever be necessary. The first orbiter spacecraft in the shuttle program was named the Enterprise. During 1977, it was thoroughly tested at Edwards Air Force Base in California. The craft was attached on top of a Boeing 747 jet plane, in the same manner in which later orbiters would be ferried to their launch sites. During the tests, the Enterprise had no power of its own. It was lifted into the air by the 747 and then released. From that point on, it was a glider, piloted by its own crew. The test flights proved out the aerodynamic handling capabilities of the craft, its control and braking systems. This was a simulation of the actual landing conditions under which the orbiters returned from space. It landed on a precise touchdown point on the runway and came to a stop in less than 10,000 feet as planned. The 747 transported the Enterprise here to the Kennedy Space Center in Florida. In the vertical assembly building, it was mated with an external fuel tank and 2 rocket boosters. It was then moved slowly atop its mobile launch platform to the launch pad. Although the Enterprise was never intended to fly into space, this is the general appearance of the orbiters when they're ready for liftoff. It's quite different from all our earlier space shots where the craft was mounted on top of a single huge rocket. In this overall view, the shuttle, ready for launching, consists of the orbiter spacecraft on top with the flight deck and the crew's quarters in the nose, the huge cargo bay just aft, and the 3 powerful rocket engines in the tail. Under the craft is a gigantic external tank containing the liquid oxygen and liquid hydrogen used to fuel the spacecraft's engines. On each side of the tank is a solid rocket booster. Liftoff. The 3 main engines of the spacecraft fire first. Then fire signals are sent to the booster rockets. 5 giant engines are now blasting away at once, producing more than 6.9 million pounds of thrust. Huge clouds of exhaust flames are deflected to either side by the concrete base platform. The entire system slowly lifts straight up, clearing the tower. At this point, the launch control is shifted to Mission Control in Houston. This cutaway view shows several unique facts about the Space Shuttle. For the first time, the atmosphere carried along is the same as Earth's atmosphere. In the living and working areas, there is a shirt-sleeve environment, and cumbersome spacesuits are now needed only outside. Because acceleration never exceeds 3 Gs, the crew and passengers don't have to be the perfect physical specimens that the earlier astronauts did. Specialists in many scientific and manufacturing fields can go along as the mission requires. 28 miles up. All fuel in the solid rocket boosters is now used up and they are jettisoned. Tiny rocket motors are fired to separate them from the tank. From here, the boosters drop on a planned course to an altitude of about 15,000 feet. After first being slowed by drogue chutes, they fall by main parachute into the ocean. A recovery crew is waiting to tow them back to Cape Canaveral for further use in another shuttle launch. Just before orbit is reached, all fuel in the external tank is used up. The main engines in the spacecraft are shut down, and the tank too is jettisoned. It also follows a planned trajectory, dropping back into the atmosphere to burn up safely or to disintegrate over the ocean. If systems for heat protection, guidance, and recovery were built into the tank, its cost would be far greater and the orbiter's payload would have to be smaller. The external tank, now just an empty shell, is the only part of the shuttle that is not reusable. The orbiter next enters orbit. Two burns are made with the maneuvering engines in the aft sections to circularize the orbit. Speed is now more than 17,000 miles per hour. The orbiter is designed to operate between 115 and 690 miles above the Earth. Its exact orbit is determined by the purpose of each individual mission. The doors of the orbiter's cargo bay are open here to reveal Space Lab inside. One crew member, wearing a spacesuit and connected by an umbilical, is at work outside the pressurized compartments. The size of the figures gives some idea of the scale of the orbiter. The cargo area alone is substantially larger than a railroad boxcar. The orbiter can carry a payload of up to 65,000 pounds. The cargo on each mission varies according to the work to be done. Space Lab, built by the European Space Agency, shown here in cutaway, is connected by tunnel with the crew compartment of the orbiter. Two scientists are at work on a busy schedule of experiments. The aft compartment of the orbiter carries a variety of cameras and other sensing equipment for Earth resources studies. The Space Shuttle is basically a money-saving space truck. In any satellite launch, the first 100 miles of altitude are the most expensive and the most critical. The orbiter gets a much larger satellite up there at less cost. By using its manipulator arm, as seen through the window, it takes the satellite out of the cargo bay and places it in orbit. Only a small engine would now be needed to boost the satellite to a much higher orbit. With little weight devoted to rockets and fuel, far more scientific equipment can be carried out to any part of the solar system. In 1978, the United States launched CSAT. Almost at once, a circuit board failed and the satellite went dead. A $70 million project had to be written off as a total loss. If the Space Shuttle had been operational then, that loss could have been prevented. Orbiter could have rendezvoused with the satellite, grasped it with the arm, and placed it in the cargo bay where mission specialists could have repaired or replaced the defective part. The satellite would then be put back into orbit, good as new. There are still two more alternatives for the orbiter in making repairs on a malfunctioning satellite. The specialists can climb into spacesuits, leave their craft through an airlock, and make repairs in the course of a spacewalk. Or if the work can't be done in space, the orbiter can pick up the defective satellite and return it to Earth for more extensive overhaul. This kind of rescue operation is one of the jobs the Space Shuttle was designed to do. The orbiter here is deploying a large space telescope with a mirror over 7 feet in diameter. Although that's somewhat less than half the size of Palomar's mirror, this instrument can see objects 50 times fainter than Palomar can because it's high above the air and dust of Earth. One of its primary functions will be to study quasars. They are the most powerful energy producers in the universe. If we could understand how they work, it could lead to the production of unlimited energy on Earth, enough to last 1 billion years. Here, the orbiter is at work constructing a communication space station of the future. The girders and antenna discs are manufactured on Earth, lifted into orbit by the shuttle, and assembled there. The station is designed to relay mailgrams for next-day delivery and to handle direct phone, television, and radio signals. Only 2 solar panels are needed for its operating power. When the assembly of the station is complete, it will be boosted out to an altitude of over 22,000 miles into a synchronous orbit. Let's say you're at a remote fishing site in Minnesota, far beyond the phone lines. This station could help you to get in touch with family and business. By carrying with you a small receiver about the size of a pocket calculator, you can be connected with any telephone anywhere. By the 1970s, America's energy problems had reached crisis proportions. Where do we turn when oil, gas, and coal are gone? Among other power sources, scientists have been studying our inexhaustible sun. These men, in the orbiter's aft flight station, are placing components for a solar power station in space. The orbiter is the tiny object in the center. The station, assembled up here, could be as much as 19 miles long. The largest type will supply enough power for 1 million houses on Earth. Solar cells collect energy from the sun and relay it to Earth via harmless microwave beams. It will then be received and distributed among existing power companies. Once the space station is operational, the power costs will be competitive with nuclear and conventional production costs. Looking farther into the future, this advanced station will support a large crew comfortably for long periods. Specialists can work here in many fields. They can use space processes to manufacture many products that can't be made on Earth, or that can be made better in space. Crystals for the electronics industry are an example. The orbiter has brought up a change of crews and fresh supplies. After the transfer, it will undock and head back to Earth. To prepare for the return, the orbiter is turned around by its reaction control engines, so that it's moving tail first in orbit. The orbital maneuvering engines are then fired as shown here, and the craft slows down and loses elevation. When the maneuver is completed, the shuttle is turned around again and it enters the atmosphere nose first. Its speed is still so great that friction with the air will boost temperatures on the nose and leading edges to about 2,300 degrees Fahrenheit. However, the craft's outer skin is aluminum, which starts to degrade above 350 degrees. Insulation was developed that consists of lightweight ceramic tiles bonded to the aluminum. They protect the orbiter from heat and, equally important, they don't wear away in showers of sparks as earlier heat shields did. The new insulation is designed to be reusable for at least 100 missions. After first re-entering the atmosphere as a rocket, the orbiter now glides into a landing at either Kennedy Space Center in Florida or the Western Test Range in California. Speed has been cut to about 210 miles per hour. Landing gear is lowered, the craft touches down, brakes are applied, and the orbiter comes to a stop. The craft is then towed to the building where its payload, Space Lab in this case, is taken out and a new payload is installed. The vehicle is fully checked out for its next flight. Then it's towed out, mated with booster rockets and a new fuel tank, and readied again for launch. The total turnaround time for the shuttle from touchdown back to launch pad, 14 days. Before the shuttle, all of America's efforts in space were devoted to solving the problems of space. How man could get there, perform a job, and return safely to Earth. We learned our task well, and the whole world watched us while we did it. The Space Shuttle opens a new era, a new generation of problem solving. Now, using our knowledge of space, we are already solving some of our problems here on Earth. After living for thousands of years bound to Earth, we have at last made the giant leap into space. In less than 10 years after our first manned spaceflight, Freedom 7 in 1961, America put a man on the moon. We went in peace for all mankind. Now and in the future, we're in space for the good of all mankind.